Good morning, good afternoon, good evening, good wherever you are, and welcome to this SNIA Solid State Storage Initiative presentation. And today we're going to be talking about an introduction to real-world storage workloads and a little about the SNIA SSSI. The SSSI is short for the Solid State Storage Initiative, reference I/O captures. So, if you're not interested in solid state storage, then you're probably in the wrong presentation. But if you are, then this is definitely the right one for you. Before we go much further, I'd just like to point out that you're able to ask questions during the session. Any questions you want to ask, Eden and I, my co-presenter, will try and answer as best we can. And you're also able to leave feedback as you leave the presentation. That would be most helpful. You can rate us on a scale of 1 to 5, where 1 is, I wish I'd been playing golf, and 5 is, goodness, that was good. I really need to do this over again. The other thing to be aware of is that you can also enlarge the screen. Some of the slides have some quite small text on them, and perhaps they appear a little small in the what appears to be a little bit of a letterbox that you have in front of you. You can, in fact, enlarge the screen to be full screen. So if you want to see some of the detail, then the detail will... Do remember that this presentation, you will be able to get a copy of the slides on the SNIA SSSI website, and I'll point you to that later in the presentation. So without further ado, let me introduce my co-presenter, Eden Kim. Good evening, Eden.
Hello, Alex. How are you today?
I'm very well, thank you. Eden is going to be doing the bulk of the work here. Now, Eden is the chair of the SSSI Technical Development Committee and the CEO of Calypso Systems. I'm Alex McDonald. I'm the co-chair of the SNIA SSSI itself, work for NetApp, and I've been doing this for some time and doing quite a lot of presentations, as some of you may already know from the audience. So, what does SNIA do? Well, SNIA does quite a lot, actually. SNIA is an organization that provides guidance and leadership in the storage networking industry. We've got 160 unique member companies that work providing this vendor-neutral education, standards, and conferences where we try and educate people in storage topics. We've got about 3.5 active contributing members and around about 50,000 IT end users and storage pros worldwide that subscribe to our newsletters, to our webcasts, and regularly visit our website. And you can learn more on our website at snia.org/technical. You can also follow us on Twitter. We've got a Twitter handle there at SNIA. Nice short one, so we must have got that one in early. From a legal perspective, I'd just like to point out that if you use anything in this presentation or anything we point you at, it's very much at your own risk. And I would ask you to respect our copyright. If you do use any of this material, then it would be really nice if you refer to, you'll see the SNIA copyright at the bottom, and it would be really nice if you actually referenced where you got the material from. So, without further ado, I'm going to hand over to Eden for the bulk of this, and Eden is going to take us through this overview of real-world storage workloads. Quite a mouthful, but Eden's an accomplished linguist, and I'm sure he'll be able to get on with it fabulously. Eden, over to you.
Okay, thank you, Alex. I'm going to go back a slide and basically give you an overview of the entire presentation. So if you get bored or you have to go away, you've got the bottom line. So when we talk about real-world storage workloads, you see it abbreviated as RWSW. I don't know why this thing keeps going forward. And when we talk about the Test My Workload website, which is where we post example captures, that's abbreviated as TMW. So basically, real-world storage workloads are unique, and they're very different from your synthetic lab workloads. And the real-world workloads change at every layer in the software stack. So the main difference between a real-world workload and your synthetic lab workload is the real-world workload is a constantly changing combination of unique I/O streams, and storage responds differently to those different combinations of I/O streams. So it's really important to know what's in your workload so that you can test your storage appropriately. And if you want to know what a real-world storage workload looks like, you can go to the testmyworkload.com website, and there are example captures posted there, and you can play with them, look at them, use the data analytics. And further, if you're interested, you can download a free applet that will capture a workload on any laptop, desktop, server that you have under a variety of operating systems such as Windows, Linux, Mac, and FreeBSD, and actually capture your workload. And then you can upload it for free and see what it looks like. So it's somewhat of an abstract concept. It's very real, but we have to use some constructs to visualize it, and that's what that Test My Workload website is for. So that's the overview. Thank you very much. If you have any questions, please send them in, and then we're going to proceed to go through this in a few 3 or 4 or 5 sections. We'll stop after each section, and then if there are any questions that have been sent in, Alex will, step in and ask the questions and we'll respond to them. Okay? So first, what are data center real-world storage workloads? So how can you analyze what a data center storage workload is? What we do is we take IO captures of those workloads, and then we look at the IO streams and the metrics that we got in the capture, and then we can further take those IO streams and metrics and create a test workload to test storage to what actually occurred on your server. So that's what we mean by analyzing data center storage workloads. So you might ask, what do you mean when you say a real-world storage workload? We're merely talking about a collection of IO streams that's seen by storage that you generate in your application space during real-world usage. Okay, so this is different than the lab workload, which is a corner case. Here, whatever you're doing on your system, we capture that activity, and we capture it at a specific level in the stack. So I've thrown out a few different terms here that may not be clear, so now we're going to look at some of the basic definitions so we can understand what we're talking about. First of all, what's an IO stream? So on the left side there's this table. Don't worry about zooming to see details. You can do that later. The main point of this table is to show you some 20 or 21 discrete IO streams that were captured during a single step of an IO capture. So when we say an IO stream, we're talking about an IO or an input-output operation that is unique. It's unique in terms of its access, it's either a random or a sequential access. It's unique in its data transfer size or block size. It's unique as a read or a write IO, and it also has a unique queue depth or number of users. So when we say a unique IO stream, a random 4K write would be a single IO stream, and a random 4K read would be a second IO stream, and so on and so forth. The purpose of the table shows you all of the discrete IO streams that we're seeing during that capture step, but what's interesting in the right-hand column, it tells you how many times they occurred. So the very first example is a sequential 1.5K write, and that occurred 63 times or 69 times over the course of that step. So it means that you can have a single IO stream occurring many, many, many times. But because it occurs 69 times doesn't mean there were 69 IO streams. There was one sequential 1.5K write that occurred 69 times. And as a footnote, you'll find terminology used in different contexts, in different domains that mean different things. There is a use of the stream definition in SSD endurance that relates to write operations that are associated with a group of associated data, and it's kind of a low-level thing that solid-state storage controllers use to optimize the endurance. In our case, when we talk about an IO stream, again, we're just talking about a unique access pattern that occurs at some level in the software stack. Okay, so you might ask, what is an IO capture? An IO capture is simply the tabulation of the statistics on the IO streams that we're looking at. So the IO capture tools will gather statistics on the IO streams. It says, oh, there's a random 4K write, mark down one of them. There's a random 4K read, mark that down. An IO capture is not an IO trace. An IO trace takes a continuous sample of all of the IOs that occur and then replays them. An IO capture is different in that it's taking a tabulation of the type of IO streams and the associated metrics that occur. So as a result, there's no data or private information collected from the target server. Only numeric tables are gathered, typically in a CSV file, and then that CSV file is processed after the fact to give you the visualization of the IO captures. So next, you might want to know what are some available IO capture tools. Well, every operating system generally has a free tool, such as perfmon is available for Windows, blocktrace for Linux, and there are also private tools such as Hiomon by Hyper.io for Windows, and the IO profiler tools, which are by Calypso, that are available on the Test by Workload site. These I/O tools differ in terms of what operating system is supported, what level the capture is taken, meaning am I capturing at the file system level or am I capturing at the block I/O level? And they differ in the type of I/O metrics that are recorded, such as are you recording the queue depths? Are you recording the response times? Are you recording the compressibility or the deduplication of the data? So these tools vary, and whichever tool you use, you want to make sure that you have a knowledge of what level in the stack that you're taking the capture and know what kind of metrics you're getting. Okay, what's the software stack? On the left side, there's an image that shows you a representation of a Windows software stack. At the top of the stack, we have the applications or the user space. At the bottom of the stack, you have the hardware or the device level where you have various storage. Intervening between application space and the device level is the software stack and the hardware stack, which is the operating system, kernel layers, every layer of cache, intelligent HBA drivers, and other abstractions that do functions such as virtualization, storage tiering, dedupe, compression, encryption, and the like. So the I/O streams that are generated in application space, in other words, when I do something, if I'm, for a simple example, in Microsoft Word and I type something and say save it, that save command goes from application space through the stack to storage. The I/O streams associated with that application step can change as it goes through the storage layers to storage and change as they go back. So we're going to talk about that as we go forward, but it's just important to know that the I/O stream composition is different at different layers in that software stack. Okay, why do these I/O streams change? Well, they change because various layers are doing something to the I/Os for a variety of reasons. The software applications or the OS kernel activities, there's metadata, caching, there's tiering. I/Os are appended, coalesced, fragmented, or merged. A lot of things happen to the I/Os as they go through the stack. An example can be if I have a random 4K write, a small fragmented block size, it may go to the system cache and reside there and then be coalesced with other 4K writes to send a more efficient 16K write to the SSD because the SSD has a 16K page size. On the other hand, if I'm doing a 1 megabyte write, a 1 megabyte file size and data transfer size is rather large, and for example, the Linux OS will typically break 1 megabyte sequential transfers into 8 concurrent random 128K transfer sizes as it goes down the stack, and then reassemble them back into a 1 megabyte file when you look at it again. So even though we're doing stuff up at application space, it's important to know that what happens when you ultimately get down to the storage can be, and usually is, quite different. Okay, so why do real-world storage affect performance? They affect performance because, as we said earlier, they're unique to what you do, and they're comprised of a constantly changing combination of I/O streams and queue depths. On the other hand, when you typically design SSD storage and the software stack, you use what are called corner case tests, which are a fixed and constant workload to evaluate areas that are outside the range of normal usage. In other words, we want to know if we hit the server with the most extreme workload, how slow will it respond, and can we plan for that corner case activity? Well, on the other hand, when we actually run a real workload, you'll find out that it's changing from every second to every second. You might have a period where you have a lot of small block random writes, then you might move into large block sequential reads, and then you'll see a period of totally mixed activity. In addition, you will see different server activity where you'll have a period of very low disk utilization or users, such as in the 2 a.m. to 6 a.m. time frame, and then you can see a boot storm or a user storm over the course of the working day. So the workloads that you see in apps application are dynamically changing, and how storage responds to this dynamically changing combination of different I/Os is very different than how storage responds to a fixed and constant corner case workload. Okay.
So Eden, before we move on to the next section, I've just got a question for you. Something you mentioned earlier. You said this isn't an I/O trace; it's just a count of the characteristic of the I/O. So in other words, privacy is not an issue. you're not collecting data from the IO stream. Is that correct?
That's correct.
Okay, good. Thank you.
Okay. Talking about IO traces and IO captures is a subject that can take a pretty long period of time, but suffice it to say that the important thing for us here is we're not taking personal data or actual user data, but when we do process the capture, we are taking a continuous capture of the IOs, and then based on the resolution that you select, we are then aggregating or organizing the data into discrete steps. So I might take a continuous 1-minute sample, but if you say I want to see it every 1 second, then we take each 1 second of activity and average it over that period. So when you look at the data or when it's visualized, I see 60 1-second data. Sorry about that. That's my CTO.
Eden, another member of the audience. I think you'll have to fix that.
Yeah. Okay. So let's look at visualization. How do we visualize a real-world storage workload? So you can visualize a real-world storage workload by creating an Iostream map. Okay, an Iostream map simply is a time along the x-axis and the number of IOs on the y-axis, and each color is a different IO stream. Remember we said that at any point you have some number of discrete IO streams, a unique size, access, and a read or write IO. So in the case here, if you look at that IO stream, you can see a blue band, a gray band, a green, orange, blue, red, yellow, and so on and so forth. So basically you have roughly 6 or 8 bands. Each band represents, or each color represents a specific IO stream. And the larger the band, the larger the percentages. So if half of the region was blue, then that blue IO stream would be 50% occurrence over that time point. So in this case, you know, you can't see it zoomed in. If you download the slides later, you can look at it. But, you know, it may be a random 4K read or 8K read or whatever, and you can see how they change over the course of the time. If you look at it, you'll see a black dominant line. That is the IOPS. So regardless of what the IO streams are, we look at how many total IOs occurred. And you can see a spike there on the left side. So there was a lot of IO activity at 1 a.m. This is a 24-hour capture, by the way. And you can see some IO spikes along the right-hand side. One thing you'll notice is that when you do an IO capture, the number of IOs you get is relatively low. It's not as if you have an SSD that advertises 100,000 IOPS. Very rarely would you see an IO value or IOPS that high, because in the real world, the number of IOs are throttled by the application. It just means that I'm only getting so many IOs based on my usage of my server. And typically the server is not being used from a storage point of view all the time. You do get bursts of activity. You may have a lot of users coming at the same time asking for information. So for a specific point, you may have a lot of users. But over the course of a large period of time, it averages out to a very low number. The second thing you should notice looking at this chart is you can see some green spikes there. There's 1, 2, 3, 4 of them, one about 40% across from left to right, and then 3 of them clustered on the right-hand side. These are spikes of a dominant IO stream, and in this case, the green are sequential half-K writes. So for SQL Server applications, just as a footnote to those that want to have some real information, sequential half-K writes is a common and prevalent IO stream component of SQL Server workloads, and the importance of that we'll see later when we look at some real data. Okay, so that's an Iostream map. On an Iostream map, you can see various secondary metrics, depending on the metrics that are captured and depending on the IO capture tool. The common metrics you take are the random or sequential access, the block size, and the read-write. Also commonly taken are average and maximum response times and other advanced metrics such as compression ratio, disk utilization, encryption, and other metrics. So depending on your tool, you can gather the things, but whatever metric you gather, it can be represented on an Iostream map. Okay, another benefit of using an Iostream map is IOs are often identified by a process ID. And a process ID is a function that the kernel does to tag an IO with the associated activity that generated it. It's not an application per se, although it can be an application, But process IDs are assigned to IOs by the kernel, and then you can grab that information and display all the IO streams by its process ID. In the example shown here, we filtered or parsed all of the IO streams to show only those process IDs that are associated with SQL Server activity. So for the 24-hour period, you would see all the SQL Server IOs, and you would see what the IO streams were, what the block sizes were, and what their occurrences were. We're going to go into this in more detail, so don't worry about that for now. So again, when we look at the visualization, four main things that real-world storage workloads can tell us are, in the upper left-hand corner, the number of IO streams that you see over the capture period. So there you see 6 different colors, which correspond to 6 different discrete IO streams. In the second chart in the upper right quadrant, you can see the occurrence of these different IO streams over time. So you can see here you have that one spike on the left-hand side or another spike on the right-hand side, and they're comprised of different colors, meaning that over different periods of time, we have different combinations of those 6 colored IO streams occurring. And also you can see when IO streams are not occurring. So after that first spike, you see there's a valley there going about a third of the way over. That's your low utilization early morning hours. In the lower left quadrant, we can see a simple representation of average response times and maximum response times. So we're looking at the response times of the IOs that were captured, and it's important to note that response times are created by all of the things in the software and hardware stack. It's not just storage. So, there might be contention, there might be multiple users, there might be, a non-disk related timeout. There can be disk-related functions like garbage collection. There's a variety of things, but suffice it to say that, from a user point of view, you just care about your overall response times, but those are overall. And then in the bottom right quadrant, the green line shows you the changing number of users, or queue depth. So this is important to know, because if I look at an average queue depth over the course of 24 hours, it could be a very low number, such as a queue depth of 4. But if I test my storage to a queue depth of 4, I will miss those times when the peaks are occurring. And in this chart, the peaks occur from 200 to 300 users over the course of the working hours. Okay, so I think that takes us to
Thank you, Aidan. So just before you
go,
just before you move on, because we've actually got quite a few questions, and I'll run through. Yes, we are going to present a copy of the slides afterwards. They will be available. And Aidan's about to give you the web address again of where you can find the IO, the tools capturing the IO stream. The question, I think, there's a really good one here, actually, and somebody says it's a silly question. No, there's no such thing as a silly question, only a silly answer. This is the question. Are you capturing IP addresses or worldwide names or IP names per capture session? In other words, how do you enumerate separate and individual workloads without capturing some form of identifier? So presumably we're capturing something, yes?
So we're only capturing the process ID or the PID in terms of identifying the source. And the other thing we capture is we capture the source or the target logical storage. So when you load the IO capture tool, it by default captures in separate containers or tables the IOs that go to all of the logical storage identified by the OS. And so one of the questions says, would you run it at the host hypervisor level, or would you run it on multiple virtual machines, aggregate those totals? The answer is yes. You can do any or all of the above. The default mode is, first of all, you select file system or block IO level, and then by default, it just captures all of the logical storage. Or you can designate a specific software level, and you can designate specific virtual machines. But the important thing to note is we are capturing at the block IO level as close to the storage as possible, because we're interested in the storage IOs, whereas a lot of other tools try to emulate the workload and create a bunch of users to simulate or emulate the workload and use that as a way to stress or evaluate their server. In our case, we're just taking whatever happened when you did it, and knowing the queue depth and knowing the IO streams and the target logical storage, we can create test workloads that will recreate that.
Okay.
Go ahead.
No, sorry, thank you for answering that question so thoroughly.
Okay. I'll just get rid of these other questions. What was the tool used to capture the IO stream being shown in the presentation? It was the IO Profiler capture tool, and that's available for free to use at testmyworkload.com. That answers the second question, how do we get the tool? And so that's it. So moving on, the SNIA SSI reference IO captures is a fancy way of saying you can go here to see some example IO captures that have been used in this presentation, are used for general SSSI educational purposes, and importantly are used by the SNIA technical working groups that are using these IO captures to develop test methodologies and specifications or technical works based on real-world storage workloads. So let's go ahead and look at a couple of things here. This next slide shows you the home page. When you go to www.testmyworkload.com, then you can click to the demo section and see 3 demo or example or reference IO captures. And more importantly, the analytics are live, so you can go ahead and click areas, you can use the tools, you can parse the workload to select subsets, you can do all the things that we talk about in this workload and in the associated white paper, which goes into great detail of what we did on your own. Secondly, you can download a free IO capture applet for Windows, Linux, FreeBSD, and Mac, and do your own capture. And basically all it is an applet that you double-click, and it asks you how long do you want to run the capture, and do you want to run it at the file system or block IO level, and what resolution do you want, and then click go. And when you're done, you get a file that ends in a .ips. You upload it to the Test My Workload site, and then you can view it. And in order to upload it, you have to create an account with your name and an email address that's valid, and then you can just upload it. We don't do anything with your data. We don't contact you, but you do agree that by uploading your workload, you're going to allow the working groups to look at your capture, and your capture can be published anonymously for the purposes of education and furtherance of our industry baseline. Okay, so if we go through this, there's a few more slides associated with this. So this is just going to reiterate what I said. What are reference IO captures? They're samples of recent user activity used by the technical work group, used for education, and there's 3 workloads that are up there. The 3 workloads, if you go to the demo page, you'll see there are 6 workloads listed on the left-hand side. Example 3, 4, and 6 are the reference workloads. Example 3 is a 24-hour retail web portal run on Windows Server 2012 at the block IO level. Example 6 is a 24-hour GPS nav portal. What's interesting about example 6, it gives you both the file system and block IO level capture, whereas example 3 gives you the block IO capture between 2 virtual drives, drive 0 and drive 1. So in example 3, you can see reading from one drive and writing to the next drive during a snapshot or during a backup. On example 6, you can see user activity in file server space, which is comprised of smaller fragmented IOs, which can go to cache, which are usually in the byte size, BYTE. Whereas at the block IO level, you see the coalescing or appending of these small byte size IOs into more traditional kilobyte size transfers, like 4K, 8K, 16, 32K, that correspond more with efficiencies of IO transfers to storage. The next slide shows us a typical Iostream map, and this should look familiar to you. This is the number 3 capture, the 24-hour retail web portal. And we're going to go back to this as we look at the data. Again, you see the A on the left is selecting the 2 a.m. spike backup, and then there's other ranges you can pick and select, and you can click and unclick the process IDs. You can click and unclick the data transfer sizes, and select whatever metrics are showing up there. There's also a way to look at this map not by IOPS but by megabytes per second, so by quantity transfer. And you can also look at an additional map called the LBA range hit map, which shows the LBA addresses that the IOs recorded to. So in other words, LBA stands for logical block address, and it's the location, the virtual location on storage where the I/O has been written. And this is of great interest to those that want to look at I/O sequentiality, I/O bursts, and spatial and temporal locality of reference, which is a fancy way of saying when and where the I/Os were written. Okay, the next slide shows me the same Iostream map, but I deselected all the colored Iostreams. So now we can more clearly see the black line, which is IOPS, and you can see the spike on the left for the SQL Server backup, and you can see the spikes on the right-hand side during user activity. We defined 4 workloads in addition to that default cumulative 24-hour workload. Workload A is that 2 a.m. spike on the left, which is comprised entirely of 64K reads and writes. B is a range, that gray box in the middle, from 8 a.m. to 5 p.m. C is evening hours, which is the little box on the right at the peak, where people are shutting down for the day. And then the orange highlighted one is the 24-hour capture, but only looking at the SQL Server IOs. And then here we have looking at drive 0. Again, remember we did drive 0 and drive 1 at the block IO level. So here when you look at it, you can just see a bunch of different colored IO streams. And if I go to the next one, it will be drive 1. So you can see that there's different stuff going to the different drives. When you download the presentation, you actually go and look at A, where you read 64K on drive 0, and you wrote 64K to drive 1, and you can look at other things. So that, I think, summarizes the reference workload section.
Okay, we got a huge number of questions came through as a result of that previous section. Let me just take you through them. I'm not going to take you through them all, Eden, because I think there are quite a few. But let's see if I can we can address most of them. Data center storage. A lot of it's not directly attached, but is based on SAN and NAS. Is this applicable to a single machine only, or can you apply it across enterprise-type workloads?
It can apply to any logical storage, which includes NAS, SAN, JBOD, JBOF, SSD array, direct attached storage, single drives, whatever you can see as a logical device can be tested. So that's the beauty of it. And in addition, you can cover a very long period of time. So a typical IO trace is very data intensive. They become very large files. You can do a 24-hour capture, and by selecting a step resolution of 5 minutes or 1 minute, have a data file size in the order of 20 to 30 megabytes as a zip file. Of course, if you go down to 1 microsecond resolution, it's going to be huge. But the trade-off is, resolution versus breadth or span of time. Yeah.
The other next question is there a tool that consolidates or aggregates multiple I/O captures? In that it's quite unusual to have a single server that provides an enterprise application.
So our I/O captures all of the activity occurring at the logical storage, which should be comprised of different applications. We can also aggregate and give a composite representation of multiple captures taken at different times or from different servers. You can run concurrent captures on different virtual machines in the same server as well. So it just kind of depends what you want to do.
Okay. When monitoring block I/O traffic, you're providing LBA information, but the question here is, let's say you've got an application that generates a block word that's 50% sequential, 50% random, but the sequential stream is to the first 10% of the LBA, and the random stream to the last 5% of the LBA range. Is that kind of information available? Can you see the difference between random to the far end of the disk as opposed to sequential to this end of the disk?
Yes, exactly. That's exactly what we do, and that's the value of it. In addition, we look at LBA activity when we have storage tiering, where 0 to 10% might be your hot tier storage, 10 to 50 might be your mixed IOs on an SSD, and 50 to 100 might be your cold storage to a hard disk spinner. And then you can actually look at the data that's laid down there and confirm if your software optimization has been effective or correct. So in other words, if we're saying all large block sequential transfers should go to LBA 51 to 100 to my hard drive, and you see them showing up on your 0 to 10%, flash very expensive storage tier, then something's wrong. So
Okay.
the short answer is yes, that's what we do with the LDA information.
Good. And the last question for this particular section, what's the overhead on capture? How much does this cost
we're very
us?
sensitive to overhead capture, and in the default mode, we are between 1 and 3% CPU usage, which is a generalized statement because we've also seen people with older machines and inefficiently set up software that no matter what you do, it's a huge impact on performance. But generally speaking, we're between 1 and 4% of CPU usage. We can also turn on secondary metrics, and this is generally done once you've taken a broad sweep and then you want to zero in on an area and do a very fine grain resolution, or turn on advanced metrics such as dedupe or decompression ratio calculations. So then you will go up. I can't say how much. It might be 10%. It might be a spike of 20%, but it's not like a 90% impact.
Okay, it's not free, but it's a fairly short piece of string.
Right, and you know, again, there's a default way to do it where we minimize impact on performance, and frankly, we use as many of the existing kernel reporting capabilities that exist in the OS. And then there's times when we do more advanced stuff that is very specific to what we want to do. And frankly speaking, much of the work with the advanced products are in response to custom requests from customers who are interested in a specific activity.
Okay. Thank you.
Okay.
Right, let's move on.
All right, so we're ahead of schedule because there was more at the front and there's less at the end. Okay, so
That's
selecting
fine.
an IO capture. So what we're doing here is now we're going back to our friend, that 24-hour retail web server, and we selected in the right-hand side in that process ID box, you can actually click unselect all, and then everything goes away, and then you click what you want. And we clicked the first box, which is SQL Server IOs. And when you click that and say apply, the Iostream Map rebuilds and shows you all of the IOs associated only with SQL Server IOs by process IDs. And it ends up being something like 78% of the IOs that we saw were SQL Server IOs. We also have an Iostream Occurrence Threshold, which means that it only shows you the IO streams that occur at a certain percentage of the time or more over the 24 hours. So the default setting is 3%. Please show me all the IO streams that occur 3% or more of the time over the 24 hours. So if you see that highlighted box there, you'll see 6 IO streams that occur between 23.7% at the top and 3.4% at the bottom. And then grayed out below that is 1.7, 1.5, and so on and so forth. So it shows you 6 IO streams that comprise 78% of the total IOs. If you were to change that IO stream threshold to 2%, you would pick up an additional couple of IO streams and increase your total percentage of IOs from 78% to maybe 80%. And you can continue to change that filter level to whatever makes sense for you. The primary purpose of putting in the Iostream threshold filter was to segregate the data so that the Iostream map would not be overwhelming. In other words, showing you many, many, many streams. In fact, if you look at it, there are a total of 395 discrete IO streams over the 24 hours. Okay, and you can see other captures where there's thousands of IO streams. Now, many, if not the majority of those IO streams are one-time occurrences of an odd size, but it's important to know that in the real world, you have occurring concurrently many, 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 many IO streams, and those streams that are small still create a, if you will, background noise that occurs. So it's helpful to sometimes look at the capture and test it with a lot of streams and then with those dominant streams in which you're interested. So again, this workload that we extracted are the SQL Server workload IO streams over the course of the 24-hour capture. There's 6 of them that are 78% of the IOs. Okay, so let's look at that a little more closely. Here you have 6 IO streams. You have a graphic representation on the left. You have random 8K writes, which is 4.4%. At the other end, you have random 64K reads, which is 30%. Note, sequential half-K writes are 28.9% of all the IO streams you saw. Okay, this is important because storage, especially SSDs, will respond differently to sequential half-K writes. Some drives are very fast at that. Other drives are very slow. Whereas for the other block sizes, drives don't have as much difference in performance. So we'll get back to that a little later. The next thing we look at here is you can take the IO streams that you just extracted for SQL Server, and you can look at all the associated metrics that were captured, and you can actually see the performance of your server during that IO capture. We call this in situ server performance. It's a fancy way of saying we're looking at the performance of the IOs that occurred when you did the capture. Okay, so the next several slides will just show you a plot or a table or a chart of the performance of those 6 SQL Server IO streams that occurred during the capture. And then when we look at testing storage, you can compare them and see that, oh, the chart that showed the in situ performance had this megabytes per second over the 24 hours. You can compare that to the same workload that was applied to test storage at a higher megabytes per second. So the first plot we're going to look at here is, well, I'll just explain what an IO self. We call that a self-test, the in situ performance of the server by taking the IO streams and showing you what performance occurred with it. So the first one is that familiar IO profile with the IO spike on the left. So we're looking at the IOPS that occurred for SQL Server IOs over 24 hours. And you can see there's the spike for user activity, there's a spike for the backup, and you can see that there's limited or low disk utilization in the early morning hours. The next plot shows you the users. We saw this earlier. The green line is the change in queue depth. So you can see that I had no users in minute 200 to 400, or very few, and then I had a lot of spikes of users during the working hours, which makes sense. So when you look at it from a user point of view and then look at the IOs, you can see here that we're showing you the IO streams that occurred and the IOPS. So you can see that the different color stacks show you the discrete IO streams, the combinations of those 6 IOs that we saw, and the dot is the IOPS that occurred at that period of time. So over here you can see there were very few IO streams, in fact only 64K, but we had a spike of IOPS up here. And then over here you can see a combination of many different fragmented IO streams and associated IO rates. Pulling out the response time metrics, we can see that response times change over the course of the capture. Simply put, when you have fewer users and fewer IOs, you usually have lower response times. And when you have more users and more IOs, they tend to go up. And then for specific times of certain types of activities or certain types of IO traffic, you'll have higher or lower IO streams. Oh, I'm sorry, response times. And then the next chart shows you, let's average out the IOPS over that 24-hour period. So before we saw a spike on the left and a wavy line going up and down. If I took an average across 24 hours, it was only 33 IOPS. Okay, but again, we had periods where nothing was going on. And you can also see where the response time, 6.94 milliseconds, was the average response time. Well, we know that the average response time is only an average, and that what we're really interested in is the maximum or the number of nines response time associated with quality of service. Same thing can be done for megabytes per second. Here we look at compressibility and duplication ratios. So compressibility and duplication is a function where the tool will measure or evaluate the data that's written to storage and calculate how much more it could be compressed or how much more it could be deduplicated. So a compression ratio of 28%, or sorry, of 4, says that you could compress this data 400 times. A deduplication ratio of 28% says that 28% of the blocks are duplicative blocks. Okay, there's more about this later. It's a whole topic by itself, but this is just an example of, depending on the IO capture tool and the metrics it captures, you can see different types of performance analysis. Okay, so that was looking at your own workload on your server and seeing the performance of the server during the capture.
So I've got a couple of questions that have come in while you've been talking. The first one, I think this is a how long's a piece of string question, but we'll see what you say. What is the ideal frequency for captures? I don't know whether that means in terms of the periodicity of the capture and the summarization level, or whether it means whether you run it daily, weekly, monthly, or whatever.
So ideal depends. If I want to get a broad idea, generalized idea of my activity, then if we're going 24 hours, there's a balance between file size and resolution. We typically use a 2-minute step frequency because that gives us a good idea of how the Iostream combinations change over time. On the other hand, You may want to know more about the I/O bursts and the disk utilization, in which case a finer grain resolution down to 100 milliseconds or maybe 10 milliseconds is desirable, in which case you should know roughly what time frame you want to capture and limit it to perhaps 10 minutes because, again, you have to multiply the number of steps times the time.
Okay, so it's a case, I suspect, of doing it for a bit at a fairly low resolution and identifying areas that might be of concern and then a bit more higher resolution during those particular periods, yes?
Exactly.
Okay. And the last question here is a really technical one. Blimey. Does the tool monitor non-read-write block I/O traffic? In other words, things like SCSI commands or NVMe admin commands. Do you count those?
So the answer is no. We're looking at logical commands to logical devices. These are more protocol level things, and so they're outside the scope of what we do. You actually want to get a bus analyzer and hook a wire up, and you want to get down to that level.
Okay, and I think I know the answer to the very last question, which is, can we replay the I/O workload using the captured workload? And I suspect the answer to that is no. It's not a replay tool at that level.
Yes, you can do that. So the way it works is you can replay what you captured, and you can also do what we call a replay test, where you take each step that you captured and you create a test script, and then you apply it to the storage. So, for example, for 24 hours, we took 2-minute chunks. So each 2-minute chunk is an I/O command, and you have, divide 24 hours, which is 24 times 60 divided by 2, and then you get that many steps, and then those are applied in the same order in which you captured them, and that's the replay test, which is coming up.
So is that a simulation or an actual replay?
Well, it's a replay of the steps. So if you want a true replay, you would have to have very, very fine resolution, and in fact, that's the difference between a trace and a capture. When you do a capture replay, you're replaying the sequence of discrete steps, so it's kind of an average of averages. So I take the average of 1 minute, and then I do every 1 minute average across time, or I can do an average of 1 second. And at some point, that average becomes effectively a replay to the level that you're interested in. But of course, the purist will say it can never be a replay unless you run it continuously. But then the other purist will say, even if you're running it continuously, you still have to have a resolution question. So it's an angels dancing on the head of a pin type of discussion.
Okay, thank you, Eden. Okay, thanks. Keep going.
So now we're getting to some data. So basically, here's a review. So we have 2 kinds of workloads we're going to create. Now we're taking that workload and we're going to apply it to storage. So remember, we have 6 I/O streams that we pulled out. We have a couple of tests where we take those 6 I/O streams and we say we're going to apply all 6 of these I/O streams together to the storage in a certain fashion and get a number. And the other type of test is the replay test, which you discussed, which is we're going to take each successive step and take that combination of I/O streams and apply it to storage and see how we do. So on the one hand, you have this fixed 6 I/O stream workload applied to the storage, and in the other case, you have a changing combination sequence to storage. Okay, those are the 2 types of workloads. So what we have is, looking at the first one, here is a summary of the next 4 slides. So you're going to see one where in the upper left, we call it a multi-write SAT or WSAT. This applies the 6 I/O streams together for every step of the test. So every second of the test is going to have the same 6 I/O streams applied to it, and you get a number. The second one in the upper right is called individual streams write SAT, which is taking those 6 I/O streams we just did the combination of, and we break them out and do them one at a time. So now we can see how well each component of that 6 I/O stream combination performed. And this is where you see, hey, sequential Haskell writes is a big game changer. That's the one that causes these drives to be different. And then the third box in the lower left is taking that same 6-stream workload in the first test, and we just apply that, but then we change the number of users. So on the left side is 1 user, on the right side is 1,000 users, and you can see how performance peaks and saturates when the users increase. And then the last box on the lower right is the replay test. This is where we take those successive combination of I/O streams and apply them to storage, and then you can see this wavy line, and you can compare the wavy line to each other to see how storage performs over the course of the capture. Okay, so the next 4 slides are just a blow-up of that. So slide number 1, again, 6 I/O streams applied continuously the same way, and you get one drive that has higher than the others, two drives that are lower. And then if I break that out and look at the individual 6 Iostreams, the highlighted ones in the middle there are sequential half-K writes, and you can see in this case, the drive in the back was 32,000 and the drive in the front was 1,800. So the drive in the back was twice the second place drive, it was 10 times the third place drive, it was 15 times the fourth place drive, and it was 30 times the fifth place drive, which means that because that workload is 30% of the composite workload, for 30% of the time, I'm 2 times to 30 times faster, so you can see how that drive is going to have the better performance. And then the third test, again, here, just looking at the same six Iostreams, and on the bottom are users, 1, 2, 4, 8, 16, 32, all up to 1,024, and the red box highlights 32 users, just because we're just picking a point to where the drives seem to peak. And this is explainable largely due to native command queuing and other design considerations that go on the drive side. But notwithstanding that, the kind of colored background box is the host queue depth range. So you can see the arrows, they go from 0 to 300. So when we did the capture, we saw a queue depth varying from 0 to 300. So here you can see you can pick any number along that 1 to 300 line, or you could just see how well the drive for this workload performs over the span of 0 to 300 users. So this is very useful, and there's additional charts here that are based on response times, which is even more critical than the I/O rate or the megabytes per second. And then the last one is the replay test. So here, because there's such a variance in the performance of the target server, the SAS hard drive, and the solid state drives, we did a comparison to the group mean. So 0 is the middle value, and there's one drive that's very close to the mean, whereas 2 drives are substantially higher than the group mean, and then 3 drives are lower than the group mean. And you can track the left to right activity with time events or with type of IOs or with processes, but this basically shows you when I replay the exact sequence and combination of IOs that were captured, you can see how storage responds to your actual workload. So it's not a pure replay test, but it's a replay test in the context of replaying the average of the averages that are represented by each discrete capture step. Okay, so that's this section. I told you it's getting faster, so maybe we'll do some questions here.
Thank you, Eden. That's very good. Yeah, the questions, well, 3 of them actually fall into the same category about workloads that are out on the website, example workloads. And the question, the 2 workloads mentioned are, first of all, is a vSAN workload, and secondly, I'm not quite sure what a deep learning workload is, but I presume it's something to do with something with a completely different I/O profile than normal. What workloads are available, Graham? Can you remind us?
Okay, so we only have a handful that are shown in the demo section. So the answer is we have not published a deep learning workload or the software-defined workload, but it's easy to do that, and we have workloads in our database for VMware and vSAN workloads, but we don't, or we're not in the business of making these publicly available upon request. If someone's interested in capturing this type of workloads, they can contact us and we can work with them to get such a workload, and if it becomes very interesting, it could be published as an example or reference workload. Okay, that's good, thank you. So I'm going to move forward to the overview slide. Just run us through the overview. Leave us here at the end, Eden, and I'll talk to people about what happens after this presentation. So it's important to understand your real-world storage workload. It's critical for data center storage, server, and SSD design and optimization. You should know what you're optimizing. Okay, you need to know the Iostreams and the software stack level. You need to find out what Iostreams actually are presented to your storage. So to do all this, you can go to testmyworkload.com. You can try the free demos. You can try out the free capture analysis tools. And you can also see some reference captures that are the subject matter not only of this webcast, but of the white paper. And when you go to testmyworkload.com, you can click to download the free white paper. And the white paper is a discussion of this methodology, which is being evaluated in the SNIA technical working groups to be a technical work, and also see the actual data as applied to 4 SSDs and a SAS hard drive using the 4 tests outlined in this presentation.
So the white paper, I believe, is going to be ready fairly soon. Fairly is a reasonable.
No, there's a white paper there now. You don't have to.
All right. Okay.
We're going to repurpose it in SNIA more towards the SNIA reference captures, but the white paper is of the data that's in this PowerPoint or this.
Okay. Thank you. I stand corrected. Okay. So thank you very much indeed, Eden. That's been a terrific presentation, and I'd just like to invite the audience to watch out for a couple of links at the bottom there. First of all, there's information on the SSSI, the Solid State Storage Initiative. There's secondly, the testmyworkload.com that Eden's been talking about today with the free capture tool and analysis that you can do. And lastly, the slides will be uploaded and available on the SSSI education part of the website. What we will also do is take these questions that we had, most of which we got to, some we didn't manage to answer, but we'll take all the questions that we've had, we'll gather those together, and we'll publish on the SSSI website a blog entry that allows you to see the answers to the questions that we've already done today and some that we didn't get to due to time constraints. But I'd like to thank Eden again for his lively presentation, and particularly the contribution of his CTO. I think he described him out as at the front of the presentation. And secondly, for the audience for being such a great audience and giving us such good questions. If you would like to mark us on the way out, I'd be very appreciative. If you go to the feedback from you give us feedback. Let us know what you think of this. Was it worth your while? Did you find it of interest? Are you wanting more information? And please let us know. As you vote on the way out, that's incredibly important to us because it allows us to tailor the kind of education that we do over the next few months as we move into this, what I think is a really exciting period for solid-state devices as we move into this period of moving away from brown spinning stuff into something that's much faster and more interesting, actually, as a storage medium than anything I've come across in the last 30 or 40 years. So thank you very much today. Thank you, Eden. Have a good rest of your day, and thank you for scoring us on the way out. Good night.